On February 27, 2026, a spacecraft older than the internet executed a routine maneuver. It was a planned roll, a slow rotation to calibrate one of its instruments. The kind of procedure the mission team at NASA's Jet Propulsion Laboratory had ordered hundreds of times over nearly 5 decades. Unremarkable, expected, scheduled. And then the power readings came back wrong. The numbers, received after a 23-hour delay at the Deep Space Network dishes in California and Spain and Australia, showed something the engineers had not predicted. During the roll, Voyager 1's power levels had dropped unexpectedly, not catastrophically. Not yet, but enough. Enough to cross a threshold that the team had been quietly dreading for years. One more drop, that's all it would take. One more unplanned power dip and an autonomous failsafe buried in the spacecraft's computer code would wake up on its own. It would begin shutting things down and recovering from an autonomous shutdown. From 15 billion miles away with no ability to respond in real time is one of the most dangerous things the Voyager team has ever had to do. They had maybe hours to decide, except their commands wouldn't arrive for almost a day. This is the story of what they did next, and what they are planning to do this summer, a maneuver so consequential that the engineers themselves have named it the Big Bang. Most people know Voyager 1 the way you know a legend. Launched in 1977.
3, 2, 1. MDS to ignition, we have a liftoff.
Roll program is in on time. Vehicle response is normal.
Bus mode looks good, tank pressures look good.
Okay, MDS. This program was in on time. Vehicle response was normal also.
Jupiter, Saturn, the pale blue dot photograph, the golden record, the edge of the solar system crossed in 2012, humanity's farthest messenger. What most people do not know is that Voyager 1 was designed for 4 years. 4 years. Jupiter and Saturn, a gravity-assist slingshot, and then the mission would be over. It was never supposed to still be operating in 2026. It was never supposed to cross the heliopause, the boundary where the sun's magnetic influence ends and true interstellar space begins. It was never supposed to become the only human-made object in the history of civilization to travel beyond the solar system and radio home. The probe weighs about 773 kilograms, roughly the size of a small car. It carries a 3.7-meter dish antenna, a suite of scientific instruments, and a single power source, a radioisotope thermoelectric generator, or RTG. The RTG does not run on solar panels. This far from the sun, solar power is useless. Sunlight at Voyager's current distance is about 50,000 times weaker than it is at Earth. Instead, the RTG generates electricity from the heat produced by the natural radioactive decay of plutonium-238. It is elegant and simple, and it has worked for 49 years, but it cannot work forever. Every year, the RTG produces roughly 4 watts less power than the year before. 4 watts is not much. It is less than the average LED light bulb. But on a spacecraft operating on a total power budget measured in the tens of watts, 4 watts per year is a slow, irreversible countdown. Here is what that means in practice. In 1977, Voyager 1 had enough power to run all 10 of its science instruments simultaneously. By 2026, after 49 years of decay, 7 of those instruments have already been shut off. Not because they failed, but because the spacecraft simply cannot afford to power them anymore. The engineering team has had to look each instrument in the eye, so to speak, and make a decision. Keep this one running or sacrifice it so the others can survive a little longer. 7 down, 3 remaining. And on April 17, 2026, it became 2. The instrument they shut off was called the Low Energy Charged Particles Experiment, the LECP. It had been running almost without interruption since September 5, 1977, the day Voyager 1 launched from Cape Canaveral. For 49 years, it measured ions, electrons, and cosmic rays streaming through interstellar space. It detected the pressure fronts and density shifts that helped scientists map the structure of the medium between stars. And in 2012, its readings were among the key data points that allowed the team to confirm that Voyager had crossed the heliopause, that it had left the solar system entirely, becoming the first human-made object to enter interstellar space. The LECP didn't just observe the universe. It helped us understand where we were in it. Its principal investigator, Stamatios Kremigis of the Johns Hopkins Applied Physics Laboratory, noted in the days after the shutdown that the instrument's sensor motor, a small rotating component designed to scan in all directions, had been tested on Earth for about 250,000 steps, enough for the original 4-year mission. By the time it was powered down, it had completed more than 8.5 million steps. It kept working at temperatures that plunged to minus 62 degrees Celsius after its supplemental heater was turned off years earlier to save power. Kremigis wrote simply, "This is the stuff that dreams are made of." The choice of which instrument to turn off next wasn't made in a panic after the February power drop. Years ago, in a display of engineering forethought that is almost painful to think about, the Voyager science and engineering team sat down together and agreed on an order, a ranked list of sacrifices, a sequence of goodbyes planned in advance, designed to preserve as much scientific capability as possible for as long as possible. The LECP was next on that list. Voyager mission manager Karim Badarudin at JPL said it plainly. While shutting down a science instrument is not anybody's preference, it is the best option available. Voyager 1 now runs on 2 instruments, one that listens to plasma waves, one that measures magnetic fields, 2 instruments in a region of space that no other human-made object has ever reached, returning data that cannot be replicated by any other mission in existence. And shutting down the LECP, according to the engineering team, buys approximately 1 year of breathing room. 1 year. But that is only the beginning of what they are planning. Imagine you are an engineer at JPL and you need to send a command to a spacecraft. You type the command, you check it 3 times, you authorize it, and then you wait. Not for minutes, not for hours. For 23 hours, the signal travels outward from Earth at the speed of light, 186,000 miles per second, across a distance so vast that the number itself becomes almost meaningless. 15 billion miles. If you drove a car at highway speed, it would take longer than the entire span of recorded human history to cover that distance. The light from Voyager arriving in Earth's detectors left the spacecraft before most of the people reading about this mission were born today. After 23 hours, the command arrives. The spacecraft processes it, and then the confirmation. The reply begins its own 23-hour journey back to Earth. Round trip 46 hours. If something goes wrong in those 46 hours, there is nothing anyone on the ground can do about it in real time. No course correction, no emergency override. Every interaction with Voyager 1 is an act of complete trust. Trust in the commands you sent. Trust in the hardware that hasn't been touched by human hands in 49 years. Trust in the software running on computers with less processing power than the device you are using to watch this video. Now understand what the Big Bang requires. The plan currently being finalized by the JPL team is to perform a coordinated, simultaneous reconfiguration of multiple systems aboard both Voyager probes. The idea is to swap out a group of powered devices all at once, shutting some components down and replacing their functions with lower power alternatives to create a new, sustainable power equilibrium that allows the spacecraft to stay warm and keep transmitting without burning through what little power remains. Staying warm is not a trivial concern. In interstellar space, the temperature surrounding Voyager is close to absolute zero, roughly minus 270 degrees Celsius. The spacecraft generates its own internal heat as a byproduct of its electronics, But as those electronics are progressively powered down, internal temperatures fall. And there is a hard limit. If the fuel lines carrying hydrazine propellant, the thruster fuel that keeps the antenna pointed at Earth, get too cold, they freeze. A frozen fuel line means thrusters that cannot fire. Thrusters that cannot fire means an antenna that drifts off target, and an antenna off target means silence. Permanent silence. The margin between Voyager is alive and Voyager is gone is at this point a narrow band of temperature, power, and pointing accuracy. The Big Bang is an attempt to widen that margin. They will not attempt it on Voyager 1 first. Voyager 2 launched 16 days before Voyager 1 in August 1977, but now traveling on a different trajectory and slightly closer to Earth, will serve as the test case. It has a little more power to spare. A signal to Voyager 2 arrives about 2 hours faster. If the Big Bang fails on Voyager 2, the team has slightly more time to understand what went wrong and attempt a recovery. Tests are planned for May and June 2026 on Voyager 2. If those succeed, the team will attempt the maneuver on Voyager 1 no earlier than July. And here is the part that almost no one is talking about. When the engineers powered down the LECP on April 17th, they left one small piece of it running. A motor. A tiny rotating sensor motor, half a watt, spinning in the dark, 15 billion miles from Earth. Half a watt is almost nothing. The power draw of a low-end LED nightlight. But it is running for a reason. If the Big Bang succeeds and frees up enough additional power, that motor could allow the LECP to be switched back on. One instrument in a region of space no other probe has ever reached, returned from the dead. Matt Hill, the current principal investigator for the LECP at Johns Hopkins, wrote after the shutdown, "We hold out hope that the Voyager engineers' latest plan will be able to power up LECP on Voyager 1 again, to let us continue to learn whatever surprises await Voyager in these distant regions of space. They have a good track record of seeming to perform miracles that stretch the remaining power supply." And then he added something honest and quiet. "But eventually this streak will end. Place yourself inside that spacecraft for a moment, not as an observer, as the machine itself. You are moving at roughly 38,000 miles per hour, drifting outward through a medium that has no name in any human language spoken before 2012. The interstellar medium. The thin, cold, nearly empty space between stars. Not vacuum in the truest sense, but close. A handful of hydrogen atoms per cubic centimeter. The faint hiss of cosmic rays from distant supernovae. The low, almost imperceptible magnetic field threading through the space between stellar systems. In every direction, nothing visible. No stars bright enough to navigate by unaided sight. The sun behind you has shrunk to a point indistinguishable from its neighbors. Just another star in the background. Alpha Centauri, the nearest stellar system, is still 40,000 years away at your current speed. Your body, the spacecraft's body, is cold. Not as cold as the surrounding space, but cold enough that engineers on Earth worry about it constantly. Your fuel lines are alive, just barely. Your antenna, a 12-foot dish, is locked on a point of light that is the sun. Every few seconds you emit a radio signal. The signal carries data about the magnetic field. The signal carries data about plasma waves. It travels at the speed of light and arrives at Earth 23 hours later, faint beyond imagination, weaker than the static from a cell phone, received by 70-meter dishes that amplify it billions of times. You have been doing this for 49 years, and now you feel the power dropping. Not dramatically. Not in the way a machine would register sudden catastrophic failures, slowly. Like a battery in cold weather, losing its charge imperceptibly until one day the margin is gone. The humans who built you are watching. They know what is happening. They have known for years, and they have a plan. Risky, unprecedented, elegant in the way that only desperation can make a plan elegant. A reconfiguration so complete and so simultaneous that they named it after the beginning of the universe itself. You wait, you transmit, you drift. Let us be precise about what is at stake. Voyager 1 is not merely a 49-year-old spacecraft approaching the end of its operational life. It is the only human-made object in interstellar space, the only probe transmitting data from beyond the heliosphere. From the region where the sun's magnetic bubble gives way to the true galactic medium between stellar systems. There is no other mission that can replace what Voyager provides. The interstellar probe concept, proposed by NASA scientists as a future mission designed specifically to explore interstellar space, has been studied and recommended by the national academies. But even the most optimistic timelines place a launch no earlier than the 2030s, with arrival at the heliopause perhaps 15 years after that. And no mission already in flight comes close to Voyager's distance. What Voyager 1's 2 remaining instruments are measuring right now, the plasma waves, the magnetic fields, is irreplaceable. Scientists studying the large-scale structure of the heliosphere, the density and turbulence of the interstellar medium, the way cosmic rays propagate through the space between stars. All of it depends on data that only Voyager can provide. The question of what happens to a human body in interstellar space is, for now, purely hypothetical. No human has come anywhere close to Voyager's distance, and none will in our lifetimes. But the question of what happens to a spacecraft there is no longer theoretical. It is being answered in real time by a machine launched when the personal computer did not exist and the internet had not been imagined, still whispering home from a place no other human creation has ever been. The Big Bang maneuver, if it works, it is estimated to recover enough power to keep the mission running through the 2030s. The team remains focused, in Badarudin's words, on keeping both Voyagers going for as long as possible. No firm end date, no switch-off scheduled, just an ongoing negotiation between physics and engineering, conducted in slow motion across a distance too large to hold in the mind at once. There is something worth sitting with in all of this. The engineers who built Voyager 1 were working without the computational tools we take for granted today. No real-time simulation, no modern programming languages. No way to predict in 1977 that the spacecraft would still be alive nearly 50 years later, still pointing its antenna home, still sending back data from a place that didn't even have a name when it was launched. They built for 4 years. The machine lasted 12 times longer. They planned its shutdown order. Years in advance, they sat in a room and agreed on the sequence. Instrument by instrument, goodbye by goodbye. Not as an act of giving up, but as an act of care. A long, patient, meticulous act of love for a machine that had outlived every expectation placed on it. And now the same engineering lineage, different people, some of them not yet born when Voyager launched, is preparing one last gamble, the Big Bang, a coordinated, irreversible reconfiguration, uploaded to a spacecraft 15 billion miles away, carrying a 23-hour delay with no ability to course correct in real time. A command that will either extend the mission or end it. They will send it anyway. That seems to be the human thing to do. Go back to the cold open, to that routine February roll maneuver, that unexpected power drop, that 23-hour silence before the numbers came back wrong. In that silence, the mission team couldn't act, couldn't fix, couldn't reach. They could only wait and plan and trust in what they had already built. 49 years of interstellar travel began the same way. A launch, a trajectory, a signal sent outward into the dark with the knowledge that by the time any reply came back, everything that could go wrong already had or hadn't. The universe is vast and cold and indifferent to timelines. But somewhere in it, a small gold foil machine is still turning its antenna toward home. And this summer, the people at JPL are going to try one more miracle. If this made Voyager feel as fragile and extraordinary as it actually is, the next video will take you to the boundary where the solar system ends and what Voyager found when it crossed it.